All right, welcome back, everybody. ET222, Fluid Mechanics. Sorry I did not make any progress last week. I had no Wi-Fi. I got Wi-Fi back for like 6 hours, but then I took it for granted thinking, oh, it'll be there. So I waited until the evening to do some recording, and then it was gone. And it's still not back at my house. So I understand the Wi-Fi comes from my local telephone company, and they provide their own power to their Wi-Fi systems. So even though my power's on, my power, I guess, is off to my Wi-Fi, my data that comes from the telephone company. So I don't get phone through them, I just get data. But anyway, it's all messed up. So I think it worked out because a lot of you didn't have power and didn't have Wi-Fi, so you wouldn't have got the recordings anyway. And so I would have been redoing it, I think. So anyway, I think it worked out. You can see here on the calendar, I now have it marked as just we lost that whole week. We are going to do some catch up. Chapter 2 was already assigned and most of you have done it, but if you've not done it, I have extended that chapter 2, 1, 3, 4, and 5. So you still have time to get that done. I think I made it all the way till Friday. Okay. This is right now our online lecture. And then you're going to do some stuff out of chapter 3, which I'm going to talk about here in a second. And then I'll do another short lecture here, probably on buoyancy. So, and we'll have our first quiz. That'll be available all day on Friday. So if that's not going to work for you, just communicate with me and we can work something out. Okay. All right, let's talk about chapter 3. Fundamental hydrostatics. So in this chapter, we are going to do pressure. We'll start with just regular fluid pressure at various depths. And then we're going to do submerged vertical, submerged inclined, and submerged horizontal, which they don't list in here. We are not going to do curved surfaces. Know that it's in the chapter, and if you need it at some point, you can look it up, but we just don't need to go there. We're not going to be swimming pool designers, I'm guessing. But if you are, it's a little different calculation if you look through that part of this chapter. But then we are going to do buoyant forces. All right. So let's just go through it a little bit. Pressure in this book is defined as a small p, and we know it's force per unit area. So any kind of pressure, whether that's underwater pressure or pressure in a tank or pressure from a structure on the ground, right? It's force per area. So that's going to end up to be pounds per inch squared or pounds per foot squared in the US system. And then it's newtons per meter squared, or kilonewtons or newtons per millimeter squared or kilonewtons per meter squared in the SI system. Okay. Now, if we start to think about pressure underwater gets developed from a column of water over whatever is feeling the pressure. So here's my little scuba diver, right? And on this person's head is this column of water. So how we get that pressure is we have to use the specific weight of water, whatever the fluid is. So if you had an object under oil, you'd need to know the specific weight of the oil in order to get that pressure, right? So for water, we just use the specific weight of water. And this column, it's like a volume, right? So really, to get that weight that is over the top of us, it is the specific weight of the water times the volume of the water. Okay? Now, that can be simplified down to specific weight times a depth z. So when they refer to depth, they call it Z. Other books will call it D, and even this book will call it D at some point. So it's kind of odd. But let's say my scuba diver here is, at some depth, we'll say they're at 30 feet, right? 30 feet of water. So that's going to become my Z. I just need this specific weight of water. So in the book, on the second page of the chapter, it talks about this weight times this volume, and that's the weight of the water over the top of you, right? And then it simplifies it out to this, because it says, oh, we can use area and force, right, for that. So specific weight is in pounds per feet cubed or newtons per meter cubed, and then volume, right? And then it says the specific weight of water is taken as this. Now, this specific weight will change based on the temperature. So I think I talked about that in this previous chapter. There's a table here, right? So if a problem gives you a specific temperature to your water, you could look it up because it does change with the temperature. So in this case, they just use what's kind of a commonly known value of 62.4 pounds per foot cubed. So foot cube's pretty big, 12 inches by 12 inches by 12 inches, right? So 62.4 pounds per foot cubed. So my little diver here, who's 30 feet deep, right, is going to get a pressure of 62.4 pounds per foot cubed times its depth of 30 feet. Pressure of, let's calculate it real quick. 62.4, 30 times 1,872 pounds per foot squared. Right? Now, it's a lot. Feels like a lot of weight when you're 30 feet deep, right? So what is it in inches, right? Inches squared. So to get to inches squared, because maybe PSI is something that we're more comfortable with than this PSF, pounds per square foot. We have to get rid of the feet. So we need 1 foot squared above and then 144 inches squared per 1 foot squared, right? So we divide by 144. So really, they're feeling 13 PSI. All right. That's maybe feels a little better because I think maybe we've all, dove down to 30 feet. 30 feet's a long ways, so maybe we haven't. But if you have, you've had to clear your ears and you've had to, you feel it, like it squeezes your body. All right, now this is a pressure above our atmospheric pressure. So here we have an atmospheric pressure, right? So there's a certain amount of pressure that we feel just walking through life. And now we're going to go down and it's going to go up 13 PSI. So for every square inch, and folks, as you know, this is a square inch right there. That's a 1-to-1 square inch. We have 13 pounds. So it's actually a lot of pressure. Now, the way it works underwater is it is on all surfaces. Now, honestly, at the lower part of your head, if you were in this position, the lower part of your head is going to feel more pressure than the upper part of your head. So it's not perfect, but most of your body is going to feel the 13 PSI in all directions. That's why we don't sink or float if we're in equilibrium underwater, which we get close to as we go a little deeper. Pressure acts in every direction, right? Every direction. Water pressure. It's very unique. Okay, but also as we're here above the water, it's the same thing. We're getting pressure in all directions on our body at all times. Okay, so that's water pressure. Now, the unique thing about water pressure, it is just dependent on depth. So if you have a pool, let's say you're at some resort and it's got a pool and then it's got a tunnel that goes to another pool, which I've seen this at a few different resorts. So it has a pool here, and then there's a tunnel, and you can literally swim underwater and go over there, right? So, and this is just concrete or structure. And this is water, water. Okay. Now, the pressure here is at a Z depth. The pressure here is also at a Z depth. And the pressure here is also at a Z depth. These pressures are all the same, regardless of whether that water column is over your direct head or not. It's over here and then it's over here. That works the same way. So if we have a pipe that's running underground, right? And here's ground. And our pipe comes up to this reservoir. So our reservoir looks like this, right? The pressure here is based on Z. The pressure here, let's say this is the end of the pipe, so it's like an opening, but it's blocked off. The pressure here is based on Z. So water's pretty unique in that you don't need the water column directly above, you just need this Z distance to the top of the water to create the pressure. So P here is going to use this Z1, P here is going to use this Z2. Yeah, so it goes regardless of whether that water column is directly above you or not. So that's a little bit unique. They have a few examples in the book that kind of show that, probably better than me. So the pressure here is going to be based on this elevation. So this is the other thing that's a little unique about this book, is it gives you a lot of the graphics in civil engineering terms. And in civil engineering, we reference elevations. So here is at the top, elevation 550, here is at the bottom, elevation 525. So the difference is 25 feet, right? So Z is going to be 25 feet. The difference between the two elevations. Okay, so be careful, look for that. It's a little different. The next thing they do is they start talking about submerged objects. So if you have an object that is at the top of the surface, this is a vertical plane, kind of like a gate or a dam, right? We have a lot of vertical surfaces. The pressure at the very top, the hydrostatic pressure, is zero. So this is the load curve, and this would be zero at the top. As you get deeper, the pressure goes up, deeper, the pressure goes up. It's linear because the specific weight of the fluid is not changing. It's the same fluid, right? So then it's just based on depth. So it's a linear graph. It's not uniform, but it is linear. And then at the bottom is their depth. So the load curve for a vertical submerged object is a triangle with one edge of the submerged object at the top. Now, if it was submerged at some depth, then the load curve is going to start at a pressure and then go to a larger pressure. So that's the load distribution But to get the full hydrostatic load, we have to simplify the distributed load. So that's something we'll practice as we move along. You're not going to need it for your first homework set, but you could be looking over this and see how they develop that into the full hydrostatic force. So F is force, and that's where we take our load curve and simplify it into the concentration. Same way here, right? Two different load distributions. If you've had statics, you understand how these distributions work and how to concentrate them. But that's what we're going to need to do to understand that force. We get an object at a slope, right? A straight, flat object laying in here at an angle. It's the same kind of curve, right? It's got a pressure here, and it's got a greater pressure down here. And it develops into a load curve. Okay? If you have a submerged inclined object, we do think about it a little differently when we go for the force horizontal and the force vertical. Because we don't really want that. That doesn't help us a whole bunch. We need to know, hey, how much down force, how much side force do we have to design for? So they kind of go through that process here. All right. Then they go on to do curved surfaces. And that gets a little complicated, kind of more complicated than we need. So know that it's here, but we're not going to do any homework in that. And that's pretty quickly chapter 13. So it has some different applications of this kind of pressure, which is interesting. A manometer uses this kind of a system based solely on water or mercury pressure. So, all right. Good enough. You're going to do, and the last part's buoyancy, and I'll do that on Friday. I think I'm doing these second lectures on Friday. So you're going to do out of the book. I'm going to show it to you in case you don't have the book yet. I think you're doing 1, 2, 3. I think just 1 through 3, maybe 4. I don't recall. Look on Blackboard to see which ones you are exactly doing. And then I will produce another short lecture on buoyancy towards the end of the week. So get the homework done, get it submitted. Reach out to me if you have any questions. Sorry about the crazy long delay week thing that happened to us last week, but that's weather. Hopefully I don't lose my Wi-Fi if this happens again, and I will produce videos from home. I just couldn't do it. Like, there was no Wi-Fi, so, and I still don't have Wi-Fi, so I can't do much, but I can at school. So good luck. Let me know how it's going and if you have any problems.